We'll start section 2 with some reviews of the course of signals and systems. We will use the same assumptions. The system is assumed to be linear time invariant and causal. We'll work with single input and single output systems in the slides in the video course, but you will see that you can work with multivariable systems in the system identification toolbox of Matlab. Well, if you make these assumptions and you know the impulse response of the system, and here we'll call it G of t. In the course of signals and systems it was called H of t. Here H of t will play a quite different role. So beware about this notation. The impulse response of the input-output relation is G of t. So if you know G of t and you know the input up to time t, you then can compute the output up to time t, and for that you use the well-known convolution integral. So in this course we'll work with sampled systems, so we need a system representation in discrete time, and this is why we sample the output. So we replace t by kts, where k is an integer, and we assume that u of t is kept constant between sampling instants. Well, this is this zero order halt method that is applied. So the signal is constant in between kts and k plus 1 times ts. So if you take the convolution integral and you replace t by kts over here and over here, this is what you obtain, right? And since u is constant between kts and k plus 1 ts, well, you can decompose this integral in, well, a sum of integrals, one going from 0 to ts, the other one going from ts to 2ts, and so on. So this one you can rewrite using a sum, and you can see over here that the index L goes from 1 to infinity, and inside here you have an integral that goes from L minus 1. You see that when L is equal to 1, it goes from 0 here to ts. This corresponds. So this is just another way to write the equation that is above. This is something that is constant, right? So we can take it out of the integral so that you write this equation over here. And so what is done over here is simply replace this integral by this quantity over here. And this is, well, what we've seen last year or 2 years ago, depends, in the course of signal and systems, right? We've transformed the convolution integral in a convolution sum. So if I write this with the notations of the course of signals and systems, what you'll have is this. Y of k is a sum. And well, here we use the index L, but in the course of signals and systems we had used n, and we had used an n that was going from 0 to infinity. But if you look at it, well, n is equal to 0 is making a direct relation between u of k and y of k. In most physical systems you will not have this, well, direct linked. It's okay, so this coefficient will be 0 in general. So you might as well start the index n at n equals to 1 and go to infinity. And then we had called it h of k u k minus n. Okay, this is the convolution sum, and you can also write it, because the convolution is commutative, as h k minus n u of k. Well, this is the convolution sum with the notations of the course of signals and systems, but here we'll use the notations of the reference book, System Identification Theory for the User. Well, this is the expression that we have found, and this is really the convolution sum that we had also considered in the course of signals and systems, but it's a bit different here because of the notations. We'll make things easier from a notational point of view by simply considering Ts is equal to 1. Of course, later when you see expressions like that, you have to remember that in the background there is some Ts there that in general will be different from 1. So if you write T is equal to K Ts, Ts is equal to 1, so this is K, and K is in N. So you can simply say that T is equal to 1, 2, 3, 4, etc. So the easiest way to see this is that, well, T is 1 times Ts, 2 times Ts, and so on. Well, if you replace KTs by T over here, right? And you now, since K is not used anymore, you replace L, the index L, by K. This is the expression that you obtain. So y of t is a sum from k is equal to 1 to infinity. So this one will simply rewrite it as g. We have the index that now becomes k, u of, well, t minus k. So this is the expression that we'll use for the convolution sum in this course. So if I write down the convolution sum of the previous slide, this is what you obtain: a sum from 1 to infinity of g of k ut minus k, and this is really the impulse response of the system. And when I say system, well, it's the relation between input and output. Okay, so what we'll do is introduce the forward shift operator. Q times u of t is ut plus 1, and the one that we'll be using quite often is the backward shift operator. Q minus 1 u of t is ut minus 1, so it's shifting to the right by 1 sample instant. So this one you can then rewrite q minus k u of t, and if you plug that in, this is what you obtain, and this is what we'll call g of q, and we'll call it a transfer function. Well, strictly speaking, this is not really a transfer function, because the word transfer function is reserved to the z transform of the impulse response, and if you use g of z, it's z transform, then you have to write y of z is g of z u z. Okay, you go to the z domain. Working with this backward shift operator allows us to write an equation like this one over here while remaining in the time domain. We'll use g of z, the z transform of the impulse response, when we go to the frequency domain, and then we have to remember the relation between z and the Laplace variable, which is TSS, right? In this course, for ease of notation, we take TS is equal to 1. Remember that S is sigma plus j omega, but if we're going to the Fourier, or if we're using the Fourier transform, then, well, we'll simply say S is j omega. In this course, we're using I omega. Okay, so we have this relation here. Z is the exponential of I omega, so there is a link between the Z variable and the variable frequency over here. So this is a notation that will sometimes be used y subscript t1 superscript t2, well, it's a data set, and it's a data set that takes all the data going from t1 up to t2. Note that the notations that are used in this course, this equation for instance, and the use of the backward shift operator is the same than the notations used in the course of model predictive control that you have followed, and that is a course given by my colleague Thomas Museur. So here are some reminders of the course of signals and systems. We can speak of poles and zeros of the system. If you talk about poles and zeros, then you have to consider g of z, so the actual transfer function. So a pole is actually a zero of the denominator polynomial, and a zero is a zero of the numerator polynomial. We can speak about stability, bounded input, bounded output stability, and we say that the system is bounded input, bounded output stable if its impulse response is absolutely summable. Okay, remember that Bibo stability means, well, that if the input is bounded, it lives here in between minus k1 and k1, then the output is also bounded. And if you have a look at the transfer function g of z, you remember that a system that is stable has no poles outside the unit circle. We'll now start the subsection on covariance and correlation. Covariance is actually a notion that you've seen last year. I've used the same slide in the course of state space control methods. In probability theory and statistics, covariance is a measure of how much two random variables change together. Here the variables will be x and y. So if large values of x tend to correspond to large values of y, well, these variables tend to show similar behavior and the covariance will be positive. Here we have the definition of covariance, okay, and E here is the expected value. So it's the expected value of x minus its mean times y minus its mean, and if, well, x and y have a zero mean, then, well, this will reduce to the expected value of x, y. Okay, well, if you take the covariance of x by itself, then you obtain this formula, and this is of course the variance, and this is something that, well, that's a concept that you know very well. Okay, in variance is the expected deviation of a random variable from its mean, and it says how far a set of random numbers are spread out around the mean. Well, the previous definition was of course for, well, scalar quantities. In the case of a vector, right, then the covariance matrix is really a matrix with, on the diagonal, well, you see that this is the variance of x1, right? So it's a matrix with, on the diagonal, the variance of the different components, and in the off diagonal terms you have the corresponding covariances. So this is the covariance of x1, x2 as defined in the previous slide. So we'll now use the notion, or define the notion, of cross-correlation and autocorrelation, which are notions that are going to be used extensively in this course, and we are relying on the notion of covariance that we have defined earlier. So the assumption here is that x and y are stochastic processes which are zero mean and stationary. Okay, this means that the underlying probability density function does not change with time. So for instance, if you take these signals and you compute the mean, the variance, they will not change with time. Okay, and if you would compute correlations, they would also be independent of time. So the first notion that is new to you is cross-correlation. Well, it's a function of a tau, and it's really computing the covariance of x with a shifted version of y, and it's shifted by tau, right? So this is really the covariance of x and y of t minus tau, and the covariance is, well, looking at the fact if x and y of t minus tau in this case vary in the same fashion, right? So we obtain a function of tau. There is a similar notion, but it's the cross-correlation of x with itself. So what you have then is the autocorrelation. It's the covariance of x with a shifted version of x, and here shifted version by tau. Okay, so we'll write the autocorrelation as Rx of tau, and we'll write the cross-correlation as Rxy of tau. Here, if we do a change of notation, t bar is equal to t minus tau, so obviously t is equal to t bar plus tau. We have here that this is really the expected value of x of t bar plus tau, x of t bar, and this is equal to the autocorrelation function of minus tau. So we see that the autocorrelation function is an even function, and this is why when we represent the autocorrelation function, we only show it for, well, most cases anyway, we show it for positive lags. So how can you compute the cross-correlation and the autocorrelation? Well, you remember that the expected value of x, well, if you have a finite set of data, can be approximated by 1 over n. The sum of t is equal to 1 to n of x of t, right? So if you look at the definitions of, for instance, cross-correlation, it's the expected value of this product over here. If you plug that in here, you find that the cross-correlation can be approximated using this formula, and this is something that you should know. Of course, we'll work a lot with Matlab, and, well, cross-correlation and autocorrelation can be implemented using the functions xcor and xcov. The second command will first remove the mean, whereas the first one will assume that the process is zero mean. So autocorrelation and cross-correlation can be used to determine the similarity of two signals and to determine the delay between two signals. We'll illustrate the first with an example in Matlab. It can also, and this is now the autocorrelation, be used to determine the period of a periodic signal, and this finds applications in synchronization of signals, echo detection, dendrochronology, as we'll see, and in this course we'll use it for impulse response identification, right? And more in particular to have an idea of the time delay. Very important in this course also, we'll use autocorrelation and cross-correlation for model validation, right? And we'll compute, if you remember, epsilon of t is the difference between the measured output and the predicted output. What we'll do is compute the autocorrelation function of epsilon of t, right? So it's r epsilon of tau based on n data, and we'll also compute the cross-correlation function of the residuals, the epsilon, with the input, and again based on n data. And we'll see later on in the course that we can use these two correlation functions to validate or invalidate a model. Well, here is a first example in Matlab to determine the period of a periodic function. So the periodic function that we'll consider is the sine of t, and its period is obviously 2 pi. So we'll assume that it is unknown and that we have to determine the period, and for that you can use the autocorrelation, and for that you're using the function x-cor, and what is computed is the autocorrelation depending on the lags. So you have three plots over here. The first plot is obviously the sine signal. The second plot is the autocorrelation function, so on the x-axis the lags, and on the y-axis you have the autocorrelation. And in the third plot you have something similar, but the lag is brought back to a quantity in seconds by taking into account the sampling period. And as you can see, and as is to be expected, well, the period of the signal is obviously 2 pi, right? And if you look at the autocorrelation function as a function of the lags, this is what you see. It's more interesting to have a look at the third plot where the lags are brought back to seconds, taking into account the sampling period. And as you can see, if the lag is 0, obviously the function correlates with itself. But you see that if you shift the signal by 2 pi, and if you compute the autocorrelation, so it's the expected value of x of t times x of t minus 2 pi, well, you have a correlation of 1, and this is so for all multiples of 2 pi. So you can use this autocorrelation function to define or estimate the period. Here the signal is a nice sinusoidal signal, no noise, so it's kind of obvious to see in the signal itself that the period is 2 pi. But if the signal is noisy, really the autocorrelation function will help. Notice that if you look at a lag that corresponds to pi, the autocorrelation is obviously -1. Well, in this second Matlab example, what we'll do is use the cross-correlation function, and for that we need to define a second signal. We keep the first signal of the first example, which was the sine of t, and we define a signal y that is defined like this. So it's kind of a sine that is modulated by a sine of 2t, and the signal is plotted over here, so in blue x and in red here y. So what we can do is compute the cross-correlation function, and this time we use the command xcov. As in the previous example, I didn't mention it, I've used the argument coef to normalize the cross-correlation, in the previous case the autocorrelation, between -1 and 1. Okay, so we can have a look. This is what is done over here in this third plot at this cross-correlation. Again, we normalize everything with respect to the sampling period so that the lags here are expressed in seconds. Okay, we see that the cross-correlation is maximum over here and it's minimum over here. Okay, so we see here that if we shift the red signal y to the right by a quantity that must be, well, approximately 0.46, you obtain this signal, and you see that you obtain now the best correlation. Okay, so the signal x and the signal y of t minus 0.46 have maximum correlation. You can see this in this cross-correlation function. So if you now go and have a look at the lag that gives you the minimum cross-correlation, it corresponds to a lag that is negative. So you need to shift the signal to the left by a quantity of, well, minus 2.68, and if you do that, you obtain the signal in yellow. And you see here that the two signals move in opposite directions, right? And well, this lag here corresponds to the case where the cross correlation is minimum. Once you have computed the cross correlation, you can use the min and max commands to automatically determine the lags that correspond to a maximum and minimum cross correlation. A nice application of cross correlation is dendrochronology, also known as tree-ring dating. Dendrochronology is based on the fact that trees produce a different ring growth every year. Ring measurements taken from trees with overlapping ages allow us to obtain tree ring growth over thousands of years for a given region. So, if a piece of wood is found in an archaeological site, the tree ring sequence is determined, and this sequence is then correlated with all the available reference sequences. This allows scientists to date and match the location of the piece of wood. In this course, we consider data-driven black box system identification, and what we'll do in this subsection is have a look at the data generating mechanism that is assumed in this course. So in the previous slides we have already looked at the relation between input and output, and we had obtained this equation over here. But of course you know that in reality there are disturbances that are always present. They could come from measurement noise, or they could come from influences on the system that are uncontrollable and unmeasurable. Well, since we're working with linear systems, what we'll do is lump all these effects together in one additive perturbation on the output of the signal, and this is what you're seeing over here and what you're seeing over here. Okay, so this first term here will express the input-output relation, and we'll see that this is a deterministic part, and what we'll do in the next slides is express v of t, and for that we'll use a stochastic framework. So as I said before, we'll be using a probabilistic framework, and the characteristic feature is that, well, nothing is known beforehand, but if you have information about past values, this might help predict future values. And the disturbance model that we'll use, which is a probabilistic description of v of t, will say that v of t is a signal e of t, and we'll define it more in the slides that will follow, but we can say that this is a white noise signal going through a transfer function. So this will be the noise model, and this relation here between e and v in terms of a transfer function can also of course be written similarly as for the input-output relation in terms of a convolution sum. Here h of k is the impulse response associated to the noise model. and the indices here range from 0 to 1. So here we assume that there is a direct link between E of t and V of t. So this is the disturbance model that we're going to use, and it looks a lot like the disturbance model that you've used in the course of model predictive control. In that particular course we had also made a normalization, and we'll make it also. We'll say that the first element of the impulse response of the noise model is 1, so that we can write h of q, the transfer function, as 1 plus a sum ranging from 1 to infinity of h of k, q minus k. So this leads to an h of q, a noise model that is monic. Monicity is also a concept that we've used in the course of digital control. E of t here is a sequence of independent, we'll define that later, and identically distributed, and we'll define that as well, variables with a certain probability density function. In practice, the probability density function that we'll use is a Gaussian of zero mean and variance sigma square, and E of t is then called a white noise sequence. So, definition of independent. Well, this means that the expected value of E of t, knowing all the values of E of t up to time t minus 1, is exactly the same as the expected value of E of t if you do not know these previous values. So the previous values of E of t do not bring you anything if you want to estimate E of t. Another way to see independence is to have a look at the autocorrelation function Re of tau, which is really the expected value of E of t and E of t minus tau. So if E of t is independent of the previous values, if you're going to take the product over here and average things out, you'll have a value of 0, at least if tau is different from 0, and it will be equal to sigma square if tau is equal to 0, right? Because we have a 0 mean here, so if you take the expected value of E squared, that's the variance, and the variance is sigma square. So if you would like to have a look at the correlogram, it will look like this. This is lag 0, and for all other lags the autocorrelation will be 0. So let's have a look at what we mean by identically distributed. By identically distributed, we mean that E of t has always the same probability density function for all times. As an example of an independent process, consider rolling a dice, un dé in French. If you define the event as rolling the dice and looking at the outcome, well, then the events are independent. If you roll the dice and you have a 6, well, the probability of obtaining a 6 the next time is still 1 over 6. So the events are indeed independent. So this is the underlying stochastic disturbance model that we'll use. Sometimes, but this is outside the scope of this course, E of t is not a purely stochastic process. It can be even deterministic or a mixture of deterministic and stochastic. But in this course, we'll stick to the previous definition. And, well, The idea of a realization of a stochastic process is also an important idea. The idea is that if you make an observation of v of t over a period of time, you obtain a possible realization of the stochastic process. If you now observe the stochastic process over different periods of time, well, the resulting observation sequences will be different in the sense that you obtain different realizations. But what all those realizations have in common is that their underlying statistics are the same. So let us have a look at the underlying statistics for v of t, and remember that v of t can be written as follows. It's a sum where k ranges from 0 to infinity of h of k e of t minus k, right? And e of t is white noise, so it's an independent identically distributed sequence, and well, the probability density function is a Gaussian. Okay, so we have a Gaussian of zero mean and variance sigma squared. So if we are interested in the statistics, what you can do is first maybe compute the expected value of v of t. So we apply the expected value on both sides, and where we have an element that is stochastic is over here. So we can write the expected value of v of t as follows. And if you take the expected values of all these elements over here, since e of t is zero mean, you obviously end up with a 0 over here. So we'll be interested in the second order properties of v of t. So we want to compute the autocorrelation function, which is the function of tau. So this is the expected value of v of t times v of t minus tau, right? So this autocorrelation function will be a function of tau. So what we'll do is compute this product over here, and again we'll use this equation. We cannot use the index k once, we have to use it a second time, so we'll have to use another name, and we'll use s over here. So if you take the product and you take the expected values inside of this sum, you'll have to take the expected value of this product over here. But remember that e of t is a, well, independent process, so this expected value of this quantity here will be 0 if t minus k is different from t minus s minus tau. So if k is different from s plus tau, okay? And the expected value of this quantity will be sigma square if k is equal to s plus tau. So all terms where k is different from s plus tau, well, they will disappear in the sum, and this is why we work with this delta function. You see that when k, in this case here, k is equal to s plus tau, this is a 1, and this produces indeed sigma square. So what we can do is get rid of this sum over here, because there is a clear link between k and s. So s is equal to k minus tau. So we keep the first sum and we replace s by k minus tau. Okay, and this is how we end up with this expression of the autocorrelation function. So we see that the second order properties of v of t only depend on sigma square and, well, the impulse response of the noise model. And you can see here that these properties, second order properties, are independent of time. So we speak of a stochastic stationary. This means really that the second order properties are independent of time process. So if we look at E of t, right, this is a sequence of independent variables. So if you look at the autocorrelation function, okay, R E of tau, then it looks like this. It will be 0 everywhere except for tau that is equal to 0, where we'll have sigma square, right? And we know also that this independence means that the expected value of E of t, if you know all the past values, and I write it down like this, is exactly the same as the expected value of E of t. Okay, so knowing the past values of E will not bring you anything to estimate the present value of E of t. Well, for V of t, things are different. Okay, and remember that V of t is a sum where k ranges from 0 to infinity of h of k E of t minus k, right? So you can see it as white noise that goes through a filter. Okay, and what you can see here is now that the autocorrelation function will in general be different from 0. So if we have a look at R V of tau, well, you'll end up with something that might look like this. Remember, it's symmetric with respect to the y-axis because the autocorrelation function is, well, even. Okay, and we'll stick to that. And also, V of t is now a sequence of variables that are dependent. Okay, and the dependence comes from the fact that, well, V of t is white noise that goes through a transfer function. And what we'll have now is that the expected value of V of t, knowing the past values of V from minus infinity to t minus 1, is different than the expected value of V of t. So this will be used in order to predict the value of V at time t, because if you know previous values of V of t, this will help you in estimating, in obtaining a prediction of V of t at time t. So here is the data generating mechanism that we are considering, and, well, the implicit assumptions that we make on this generating mechanism. So we assume that the input-output data are generated according to this equation over here. So y is the sum of two parts. The first part that comes from the deterministic part, and a second part, V of t here, which comes from a stochastic part. So V of t is modeled as white noise that goes through a transfer function. So G of q is the input-output transfer function, right? You can write it in terms of the impulse response. So if you put an impulse at the input here, and you put E of t is 0, that and at the output you'll have the impulse response. And from the impulse response you can construct the transfer function, right? And here k ranges from 1 to infinity, because we assume that in a physical system there is no direct feed through between u and y. Well, H of q, the noise model, can be written in terms of the impulse response of the stochastic part. So then you have to take u of t 0, you put an impulse at the input, and the resulting response is this impulse response here, h of k, that you can link to the noise model as follows. Here k ranges from 0 to infinity, so there is really a feed through. So y of t is directly influenced by e of t, and this direct influence is actually h0, and we say that it is 1. So this is this normalization, and this makes sure that h of q is a monic transfer function, right? And then we still have to talk about E of t. E of t is white noise, and what we mean by this is that the data is, well, a sequence of variables that are independent. They are identically distributed according to a Gaussian distribution with zero mean and variance sigma square. So we'll illustrate this in the case of a purely stochastic ARMA process, and what we mean by an ARMA process will be explained later on in the process. For the moment, it suffices to know that this is really the noise model, and that this noise model is really a transfer function with on the numerator a C polynomial and on the denominator an A polynomial. E of t here is, well, white noise, okay, and the mean is 0 and the variance is 1, okay. So this type of process is generated using this equation here, okay. So how do we see this? Well, we see that A of q yt is equal to C of q et. So we have 1, so let's say y of t minus 1.5 y of t minus 1, right, plus 0.7 y of t minus 2 is equal to e of t, right, minus e of t minus 1 plus 0.2 e of t minus 2. In this case, since the process is purely stochastic, y is equal to v. So if you replace y by v and you take these terms and you take them to the other side, you obtain this equation here. Well, remember that e of t is a sequence of independent variables, but when you look at this equation here, you can clearly see that v of t depends on previous values. So clearly v of t will be a sequence of dependent variables. So what you can do in Matlab is generate a sequence of length 1000 of e of t using the command norm rnd, and this will generate a sequence of independent identically distributed Gaussian white noise. So this is really one realization of e of t. And then what we can do in figure 1 here is look at the autocorrelation function, and we should see that this autocorrelation is equally 0 everywhere except in tau is equal to 0. So what we'll do is use a noise model. Remember that it's the transfer function c over a, and here are the two polynomials, and what you can do is have a look at the Bode diagram of this transfer function here, and here it's kind of assumed that ts is equal to 1, and what we'll do is filter e through this transfer function. This can be done through the filter function, and what we'll do again is now look at the autocorrelation function, but this time the autocorrelation of v here, and I didn't tell you before, but what we'll do here is use the command xcorr again with this argument so that everything is in between -1 and 1. And then we can look at this, well, autocorrelation of v of t, and now we should see that the autocorrelation is different from zeros in general. So what we see here is the autocorrelation function of e of t. It is as expected. Well, it's approximately 0 for lags that are different from 0, and it corresponds to the variance, which is 1 in this case for a lag of 0. You see that the autocorrelation is not exactly 0 for lags different from 0. This is because we compute the autocorrelation based on a finite number of data points. If n increases, you will see that these values will become smaller and smaller. So what we have represented over here is the autocorrelation function of v, again based on n data points. And well, as expected, we see that this is really an even function of tau, so we could represent it only with positive lags and imagine the rest. But you can see now that the v of t are correlated with previous and future values, okay? And this is because, well, v of t is generated through an equation in which you see clearly that v of t depends on v of t minus 1, v of t minus 2. Okay, so this results in a correlogram that looks like this. So remember that e of t is a white noise, so it's a stochastic signal, but it also has the property that the intensity will be equal at all frequencies. So we say that, well, the signal e of t has a so-called flat spectrum. This is why it's called white noise. So remember that v of t is obtained by filtering e of t through a filter h of z, and what we see over here is the Bode diagram of h of z. So what will happen is that in certain frequency ranges there will be amplification, right? And in others, well, there will be attenuation. So v of t will be called colored noise. Its spectrum will not be flat anymore. Well, in the previous examples we have looked at autocorrelation, so what we'll do now is look at cross-correlation. So we have still a white noise signal e of t. V is obtained by filtering e of t through this transfer function c over a. And then what we do is have a look at the cross correlation between E and V, and the cross correlation between V and E, right? So here we use the command xcor, but you could also use the command xcov. So let's have a look. So what you see over here is our e v of tau based on n data, and really this is 1 over n, a sum over all the data. Well, let's write it, it's t equals from 1 to n, and then e of t v of t minus tau. Remember that v of t is h of q e of t, right? So v of t depends on past values of e of t, right? This is simply coming from this filtering. So if you take a tau that is positive, what we'll do is shift v of t to the right. So if you correlate, well, you'll take e of t's coming from the future. So obviously we'll have this value of the cross-correlation, sorry, be approximately 0. Okay, and if you take t is equal to 0 or t negative, well then, since you're going to shift v of t now to the left, it will correspond to past values of e of t, so there will be some cross correlation, right? So in general it will be different from 0, except if you take lags that become too negative, because there you lose the correlation, right? So here to the right we say approximately 0. This is again because we compute this cross correlation based on a finite data set. If you would increase n, these values would go to 0 with n increasing. So here we look at the cross correlation between v and e. So we look at r VE based on n data, and again it's a function of tau, the lag. So we have 1 over n, a sum where t ranges from 1 to n, v of t, e of t minus tau, and of course v of t will correlate with past values of e of t. So if you take tau larger or equal to 0, what you'll have is that you'll shift e of t to the right, so that v of t will correspond with past values of e of t, so there will be some correlation. So in general r v e of n will be different from 0. And if you take tau negative, okay, well, since you shift e of t to the left, well, there will be no correspondence with, well, between values of v of t with past values. So r v of e will be approximately 0. It's approximately because we are using a data set with n values over here. So what you see here is that you have kind of a reversal here with respect to the previous situation. So you can write that RVE of tau based on n data is equal to REV of minus tau based on n data. So what we can do over here is look at an even simpler example where v of t is generated as follows. So e of t, and this is h of q. So if you multiply by the a polynomial on the other side, so we'll have 1 times v of t, so v of t, plus a times vt minus 1 is equal to e of t plus cet minus 1. So v of t is obtained as minus a vt minus 1 plus e of t plus cet minus 1. So what we can do is play with the coefficients a and c. Well, construct v and then look at the autocorrelation function and see what happens. So we'll start with very small values of c and a, and if you look at the transfer function, well, it means that the transfer function, the noise model, is approximately 1. So v of t and e of t are approximately equal. So if we look at the autocorrelation, you would expect to see an autocorrelation that corresponds to white noise, which is 0 everywhere except in tau is equal to 0. And this is indeed what you see. So now we have increased both a and c by a factor of 10, and we see that we start to introduce some correlation between the v's. You see that there is a correlation between v and v of t minus 1, for instance. So we have further increased the values of a and c, at least in absolute value, here by a factor 10 again. And this is the correlogram that you obtain. You can see here that now clearly there is a strong correlation between the v of t and its past values. Okay, and remember that this is because we have v of t is equal to minus a v of t minus 1 plus e of t plus c e of t minus 1. So if, well, minus a becomes a value that is close to 1, we'll introduce a very strong correlation between v of t and the past values through this equation. So we can also have a look at what happens if we put a positive value over here. Then we'll have something that looks like this, and again this can be explained through the fact that v of t here is now minus a vt minus 1, and this is now a negative number. Okay, so this is why you see these alternating signs here appearing in the autocorrelation function. Okay, we had something similar in the impulse response. Well, in this subsection about frequency domain expressions, there are quite a few slides that I have to skip because we only have a 15-hour course. So I'm trying to give you a rough idea of things. We've talked about stationary stochastic signals, and stationary stochastic signals are signals for which the second order statistics are independent of time. So we have to look at the covariance function, sometimes called also the autocorrelation function, the cross-covariance function or the cross-correlation function, and well, if these processes S and W are stationary, right, well then these quantities are time independent. So, of course, we do not work only with stochastic signals, we also work with deterministic signals. And if you have a look at it, well, a deterministic signal is in general not stationary. Take simply a step signal and look at the expected value of this step signal. At first it will be 0, and then it will start to grow until it reaches the value of half the amplitude. So you can see here that the expected value is time dependent, so this cannot be a stationary signal. So in the book, in the reference book, they came up with this concept of quasi-stationary, and it's a more general framework so that particular concepts become applicable to deterministic signals as well as stochastic signals. Well, without going into the details, a signal S of t is said to be quasi-stationary if, well, its first order statistics, second order statistics are bounded. So if you look at the step signal that we had considered before, right, and if you look at the expected value of S of t, well, it will change with time, but it will be bounded. So a step is indeed a quasi-stationary deterministic signal. If you would look at a ramp signal, then of course you see that, well, the expected value of this ramp signal will be growing with time, and it is not bounded. So a ramp signal is not quasi-stationary. Assuming quasi-stationary signals, you can define what is called the spectrum of a signal, and it's defined from its autocorrelation function, and here is the formula. And you might remember from your course of signals and system that here the spectrum is the Fourier transform of the autocorrelation function. You can see here it's not mentioned that it's the discrete time Fourier transform of the autocorrelation functions. This goes beyond the scope of the course, but you can also define a cross spectrum between two signals, and there you need the cross correlation function RSW of tau. So we have defined the spectrum of a signal in the previous slides, and remember that it's linked to the Fourier transform of its autocorrelation function. So let's have a look at a stationary stochastic process V of t that is constructed as, well, defined before. So it's white noise that is filtered. Well, you can compute its spectrum, and it's given over here. So the idea of this formula is that, well, you start from the spectrum of E of t, which is really flat. It has the same intensity sigma square at all frequencies, and while E of t is filtered through H of q, the resulting spectrum of V will be modulated by the module of H of z, evaluated at z is the exponential of I omega, and then this module is squared. So there will be frequency ranges where, well, there will be amplification, and other ranges where there will be attenuation. So remember that the modulus of A squared is equal to AH conjugate, right? So phi v can be written as follows. It's sigma square, and then we take H of z multiplied by its conjugate, but the conjugate will be H of z minus 1, right? Because we work with z, and we evaluate z at the exponential of I omega. So taking the complex conjugate is simply taking z minus 1, right? Here there is a very important remark, because we can work with an H of z, so a noise model, where without loss of generality we can take the poles and the zeros inside the unit circle. Well, let us take an example. If we, for instance, take an H of z where the zero is outside the unit circle, so it's at 4, so it's clearly outside, and we'll keep the pole inside the unit circle. Then to compute the spectrum, we'll have to consider H of z minus 1, so z minus 1 minus 4, and z minus 1 minus 0.5. So this is 1 minus 4z, and this is 1 minus 0.5z, right? So we multiply these two, we replace z by this quantity over here, and we have the spectrum. Well, you can see that instead of taking this noise model, we can take H1 of z, which is equal to 1 minus 4z over z minus 0.5. Okay, with the advantage now that the zero is inside the unit circle. The pole was already in the unit circle. So if we now write h1 of z minus 1, right, to compute the spectrum, we have 1 minus 4z minus 1, we have z minus 1 minus 0.5, so this is equal to z minus 4, 1 minus 0.5 z, right? So to compute the spectrum, if we take h1 of z times h1 of z minus 1, we have exactly the same thing as with hz times hz minus 1, right? We'll generate exactly the same spectrum. So without loss of generality, you can always find a noise model where the poles and the zeros are inside the unit circle. This is important because we want a stable transfer function, but we'll see later that we also need a inversely stable transfer function, so that we take the inverse of h. Well, if it has zeros inside the unit circle, it will be a stable transfer function. So let us apply this on an ARMA process that is described by this equation over here. Using this backward shift operator, we have this equation, right, is equal to e of t plus cq minus 1 e of t. And if we rearrange this, this is what we obtain, where h of q is the transfer function. So what we'll do is write sigma square h of z minus 1 times h of z applied in z is equal to exponential of I omega. So this is here h of z minus 1 applied in z is equal to exponential of I omega, right? And this one here is, well, h of z, right? This is 1 plus cz, 1 plus az evaluated at z is equal to exponential of I omega. And if you do the calculations, this is the spectrum that you have. So you see that the original spectrum of E was flat, but the one of V will not be flat. It will actually be a function of omega. So what we can do now is use Matlab to compute the spectrum, and what we'll do is also compute the Bode diagram of the noise model, which is 1 plus CQ minus 1, 1 plus AQ minus 1, so this is HQ, and we have chosen particular values for C and A. In the last plot, we'll have a look at the impulse response of the system, and we'll compute it from the transfer function. So what you see over here is the spectrum of V that we have computed for these particular values of C and A. Remember that we have started from a flat spectrum, so the spectrum of E is flat, and here you see the spectrum of V. So you see that in the low frequencies we have had amplification and we have had attenuation in the high frequencies. So if we have a look at the Bode diagram of H of Z, this is what you have, and remember that phi of V is sigma square, and then you have the modulus squared. Okay, so you take this thing here, this is the modulus, and you have to square it. So phi of V can easily be constructed in this case from the Bode diagram. Since we're working in dBs, if we're squaring, this will simply amount in doubling the value in here, and we'll have to multiply by sigma square, but in this case sigma is equal to 1. So indeed, sigma is equal to 1. To obtain the spectrum of V, we'll simply have to double what we see here in the magnitude part of the Bode diagram. And this is indeed what you see over here. So this is the impulse response. Let us check that. Remember that h of z is equal to 1 plus c z minus 1, 1 plus a z minus 1, right? Well, the inverse z transform of 1 plus a z minus 1 is, well, minus a to the power k, and then we have to use the step function or the Heaviside function. I cannot use u here because it's the input, so I'll write it down as Heaviside k, right? So if we want the impulse response, we have to do the inverse z transform of h of z. So what we'll have is, well, this term over here, minus a to the power k, Heaviside k, and there will be, well, the same term here, but times c times z minus 1. So we'll have plus c minus a, but to the power k minus 1 right now, and we have to take the Heaviside function in k minus 1, right? So we can, and this is really h of k. So we can have a look at h0, it's 1. When k is equal to 0, this one is not going to be contributing because this one is going to be 0. So we'll have minus a to the power 0. So it's a 1 over here. So this corresponds. This makes sense because our transfer function is monic over here. So we have this normalization. h0 is equal to 1. We can have another look at, for instance, h of 1. So this will be producing minus a, and here you'll have plus c with minus a to the power 0, so this is 1. So in our case over here, this is minus 0.5 plus 0.8, so this is indeed 0.3, so this is correct. So previously we have looked at the spectrum of a stochastic process. Now we look at the spectra of mixed processes. So S is u of t plus v of t. U is a deterministic sequence with spectrum phi u, and v of t is a stochastic zero mean process with spectrum phi of v, and this is important. We assume that u and v are uncorrelated. Well, then you can obtain the spectrum of S by simply adding the spectrum of u and the spectrum of v. So far we haven't looked at spectra of signals that are really the result of a filtering operation of a, well, deterministic signal. So here we assume that u of t is quasi-stationary, and we have defined this previously, and that, well, u as a given spectrum phi of u, and what we consider is y of t is equal to g u. So y is obtained by filtering u through this transfer function, and obviously we'll assume that the filter is stable. Okay, then what you can obtain is that, as a result, is that y of t is itself a quasi-stationary filter, and it's possible to compute the spectrum as follows. So what you have here is the modulus of g evaluated in z is equal to the exponential of I omega, and you have to square it times the spectrum of u. So you can influence the spectrum of y by influencing u, and well, depending on g, there might be regions of frequency where you either will amplify the energy that you have in u or attenuate the energy that you have in u. So we arrive at the final result. Remember that this is the equation that will be generating the data, as we have assumed previously. We'll assume here that u is a deterministic but quasi-stationary signal with spectrum phi of u. This is the noise model. This is the deterministic part, the stochastic part, and we'll assume that both g and h are stable filters. In the remaining part of the course, we'll use also the fact that without loss of generality, h is also inversely stable. So here is a E of t is a sequence of independent, identically distributed white noise. Okay, so this means that the probability density function is a Gaussian distribution with zero mean and variance sigma square. And then now we can combine the results. Okay, so the spectrum of y will be the spectrum of the deterministic part. We've just seen that this is what you have to use, and we'll have to take the spectrum of v, and this is v over here, and we have seen that the spectrum of v can be written like this, right? I didn't mention it in the previous slide, but you can also define or construct the co-spectrum, but this is outside the scope of the course, right? So if you look at y, you can look at its frequency content and you can kind of see where it's coming from. Well, it can come from an amplification of some sort in the noise model, okay, because you start with an E of t with a flat spectrum. It can come from the input, right, because the spectrum of u is in general not flat. But even if you have some frequency content in u, well, it can be amplified in some regions and attenuated in others through the transfer function of the system. So remember that y here is a mixed process. So here we have the deterministic part and here the stochastic part. And in order to write the spectrum of y as the sum of the spectrum of this signal plus the spectrum of this signal, well, these signals had to be uncorrelated, okay? So this means that, well, basically the data have to be collected in open loop. So this is the situation that you have. So you have g of q over here. We'll put h of q over here, e of t, u of t, and then you have a summation over here, and what comes out is y of t. So in this situation you can write the spectrum of y as follows. If there is feedback in the system, that you have here a controller, let's call it c of q. Well, in this situation we have things that are changing because u and e are now correlated through the feedback. So then in this case, well, the expression of the spectrum of y would be different to what is written over here, and the expression becomes more difficult, more complicated.